Hey guys, we haven't had a lecture in a while. So we are finishing Unit 5 it's actually the lecture that we were supposed to start with. Mrs. Stroik and I kind of had put it off because we were hoping we'd get back to school. There's some math in this one. So some of the stuff's going to be like, oh, like, why didn't we learn this before we did renewable and non-renewables? Well, we were supposed to. So I'm going to go kind of fast because it's stuff that you should probably actually know. So you should have your reading guide. It's a single sheet, environmental, nope, energy, concepts, and consumption. This is chapter 2. Let's do it. Let's move me down there. All right, so first we kind of have to define energy. That's what this whole unit was about. You probably learned this in physics, maybe in chemistry. So number 1, defining energy is the ability to do work. And when you're talking about energy loss and energy efficiency, that also means transferring heat, right? So, like, every time we convert one form of energy to another, we're going to lose some as heat. So, kinetic energy, this is number 2. Kinetic energy is energy of motion, energy of movement. We'll put all that up there. So, examples: flowing water, a car driving down a freeway, electricity. What's moving when you talk about electricity? It should be electrons flowing through a wire. Wind is kinetic energy, water moving through a dam. I think I said that already. All right, so that's energy of movement. We'll get back to potential energy in a minute, but heat we're going to define as, are you ready? The total kinetic energy of all moving atoms, ions, or molecules in an object. The total kinetic energy of all moving atoms, ions, or molecules in an object. So that should be number 3. Number 4 asks about electromagnetic radiation. And we're talking wave energy. So the spectrum. So examples, microwaves, gamma rays, UV radiation, X-rays. Okay, that's all for number 4. Back to number 2 then, potential energy is stored energy. So it has the potential to do work. That's what it's kind of talking about. That's why it's named that way. In physics, you learned about gravitational potential energy. So if I have this banana, right, and I'm holding it and I drop it, which I won't because it's our last banana and that would ruin it. When I'm holding it, it has gravitational potential energy. If I had a spring that was compressed, right, that's a different kind of potential energy. The banana also has chemical potential energy. If I would peel it and eat it, or feed it to my pet monkey, right, that we could break down the banana, break the bonds chemically, and release energy to power our body. So potential energy is stored energy. It can be changed into kinetic energy. So once upon a time, before COVID-19, we had a quiz on this stuff. It would have been your chapter 15 quiz, would have also included this, and there was a short answer where you had to, there was a situation and you had to write about what types of energy were there. And it was like, dude sitting under a tree and an apple falls on his head. Like, what types of energy are there? And people talked about the moving apple is kinetic. The apple in the tree is gravitational potential. The apple itself is chemical potential. Okay, so be ready to discuss that in an FRQ. We will not be giving you one on that, but who knows what they're going to be giving you in about a month. Here's another kind of picture that you should be able to describe. So this is the reservoir side of a dam in Tennessee, like Tennessee Valley Authority. Electricity. Water stored in here has potential energy, which then can become kinetic energy. When water flows through those channels built into the dam, it spins a turbine to produce electricity, moving electrons, kinetic energy. Okay? So just energy in general. So you all did presentations a couple weeks ago on renewable energy. Renewable energy is gained from resources that are replenished in a relatively short amount of time. That was a question on your quiz, actually. So replenished within our lifetimes. Non-renewable energy can be depleted, and they're not replenished by natural processes in terms of human time scale. So this is number 5. We're on to number 5, okay? So examples of renewable you should know. You should be able to list all 6. Solar, wind, solar, wind. hydroelectric, geothermal, biomass, and hydrogen fuel cell. And then our non-renewables that you should know, petroleum or crude oil, natural gas, nuclear, and coal. What's our dirtiest burning fossil fuel? Does any of the Simeks know? The Simeks all have their headphones in. All right. All right, so you see our petroleum there. You see coal in the middle. That's our dirtiest burning fossil fuel. And you see natural gas right there, which makes me hungry because it's lunchtime. Good. So moving on to number 6, you should be able to fill it in from this picture. You should also add nuclear. So when we're talking energy quality, we're talking about the measure of the capacity of that type of energy to do useful work. And it goes along with EROI, which you might have seen mentioned when you did your research, energy return on investment. It also goes along with net energy yield. Remember your energy yields. You've got coal, that's high energy yield. You've got natural gas and petroleum, which are medium. Solar's medium. Okay, so think about that when we talk about energy quality on the next slide too. So we are on to number 7. High quality energy has high capacity to do work. It's concentrated. Okay, so we're talking about high temperatures. We're talking about strong winds. We're talking about fossil fuels that when you break those bonds, those hydrocarbon bonds, the carbon-hydrogen covalent bonds in the hydrocarbon chain, it releases a lot of energy in a small amount of time. So that's concentrated energy. Concentrated sunlight even. Why are you looking at me? No. You're yelling. Low quality energy has not a lot of capacity to do work. So not all types of energy can be harnessed. Okay, so it's more dispersed. Oh, I don't want to go on there. So you have, like, think about the ocean. You have this enormous, almost infinite amount of molecules moving around in the ocean, but it's so spread out, like it's so hard to harness that. Or think about just like air in general. So you have this low quality energy, low heat, just not super useful. So when it's spread out, it's hard. It's not concentrated. It's hard to harness that to do work. So then the last thing is Newton's laws of thermodynamics. Actually, they're not Newton's. Newton is motion. These are just laws of thermodynamics. So that first law, which if I was in class with you, I would say part of it and you would finish it for sure, is energy is neither created nor destroyed but can change form. So it's that law of conservation of energy. We can transfer from one type to another. We may lose some as heat. We will lose some as heat. But that energy is transferred. It's not made and it's not destroyed. Okay, so we are on number 8. Number 9 then is a little more abstract. The second law then talks about how when you're changing from one form to another, you're always stepping down in terms of energy quality or usefulness. We're always losing some as heat, and it's always becoming less and less concentrated. Always. Okay? So energy always goes from more useful to less useful form. And the word that kind of goes with that is entropy or disorder. So entropy, E-N-T-R-O-P-Y. I don't have my stylus, otherwise I'd write. I don't know where it is. Entropy is always increasing. Okay? So that's kind of the basic structure of the energy lecture. We are going to be doing energy math the rest of the week. I've got some problems for you that are also on your reading guide, but I'm going to do that in a different lecture so that you can just focus on the math. All right? Have a great day. Mm-mm-mm.